and welcome back to Data-Driven Methods in Dynamical Systems. And today I want to talk to you about an inner product space that me and my colleagues have developed for the analysis of dynamical systems, specifically dynamical systems that give rise to densely defined Liouville operators. And this involves occupation kernels, Liouville operators or Koopman generators, and reproducing kernel Hilbert spaces. So inner products are absolutely essential for everything dealing with machine learning and approximation theory. And in particular, given a collection of basis functions, you can make a span of these basis functions, and if it's a finite collection, then this gives us a closed subspace of an inner product space, or a Hilbert space. In general, what we have is we have a function that is outside of the span of the basis functions, and we want to find the weights that give us the best possible approximation to that outside function according to this basis. And the determination of these weights turns out to be a rather simple algorithm involving what is called the Gram matrix. Now, sometimes we don't even have to deal with the Gram matrix in order to compute these projections. For instance, when we took a look at the Paley-Wiener space and we considered the sinc functions, we saw that the sinc functions formed what is called an orthonormal basis for the Paley-Wiener space. That meant that if we had a function inside the Paley-Wiener space that we want to express as weights against the sum of this orthonormal basis or these sinc functions, all we had to do was take the inner product of f against these sinc functions, and then that would give us this expression for f. And it turned out that this inner product is simply the sample of f at a particular point in its domain. And this led to the Nyquist theorem for band-limited functions. Now that worked out really well when we're trying to get a direct approximation of the function from samples. Now, in this setting, we're not going to have quite as clean as samples of a dynamical system, where with a regular function approximation scheme, we are going to be trying to use the direct samples of our functions. We don't have access to the direct samples of our dynamical system. We have access to trajectories. And so what we're going to do is we're going to devise an inner product based on these trajectories in order to compute the weights for the projection. Now, in order to actually compute this projection, we're going to reduce this problem down to a parameter identification routine that gives us a weak formulation of what is called the Cindy algorithm by Coutts and Brunton. But before we get there, we're going to have to take a look at, well, inner product spaces. So, inner products and projections. So on the easiest level, we're trying to project down onto a plane, say out of 3 dimensions or something like that, or even with a movie projector onto a screen. We are trying to take all the information in 3 dimensions and slam it down into 2 dimensions. And in order to do that, we're going to take these vectors that define our plane, and we're going to go ahead and compute the Gram matrix. So say these vectors are, say, u1 and u2, and then the Gram matrix that corresponds to these vectors is going to be u1 interproducted with itself, u1 interproducted with u2, u2 interproducted with u1, and u2 interproducted with itself. And then what we want to do is we need to take that outside vector and take its interproduct against u1 and u2, and then invert this Gram matrix against it, and then that gives us the weights that need to go on u1 and u2 in order to get the projection of that outside vector down into our plane. And you can extend this to any number of basis functions and sort of hyperplanes and other things like that. And it extends not only out of, say, R3, but to any Hilbert space. So if I have a dynamical system F, what we're trying to do is find its projection onto a collection of basis functions according to a new inner product. So we're pretty close to the theoretical foundation that we need for this inner product. So last time we talked about these Liouville operators, which are sort of this orbital derivative approach on a Hilbert space, where we take a function g out of our Hilbert space, and we take a look at the gradient of g of x times our dynamics f of x. And this formal expression is an operator on a Hilbert space with a very particular domain. Now, with this domain that I have displayed here, it is a closed operator, and so that means that it's going to have a well-defined adjoint. And this adjoint is going to be densely defined, provided that the original Liouville operator was densely defined. And we talked about a few cases where that can end up happening as well. Now, if we take an occupation kernel, which corresponds to a trajectory from the dynamical system, then we know that the adjoint of the Liouville operator acting on this occupation kernel ends up being a difference of 2 endpoints of kernels, where that occupation kernel represents the functional, where if you take a function and you interproduct it against this occupation kernel corresponding to our trajectory, the ultimate result is that you have the integral from 0 to t of g composed with gamma of t dt. And so ultimately we see that if we are taking a look at the Liouville operator corresponding to the dynamics f, acting on g and take that inner product against this occupation kernel, the ultimate result is the integral of the time derivative of g composed with gamma of t, and so ultimately this is a difference of g evaluated at the two different endpoints of the trajectory. This means that the adjoint of our Liouville operator acting on our occupation kernel is a difference of kernel functions at either endpoint of our trajectory. The one thing I haven't told you yet is what happens when the symbol of our Liouville operator, the dynamics that give us this Liouville operator, don't actually correspond to the trajectory at all. And this sort of computation is going to be necessary in order to compute the inner product. Okay, so let's go into the critical step for this entire inner product space, and that's compute the adjoint of a Liouville operator on an occupation kernel where the trajectory doesn't necessarily match up with the dynamics themselves. Now, to find this adjoint, of course, what we're going to have to do is we need to take a look at the functional g maps to a sub y of g interproducted with this occupation kernel corresponding to gamma. We'll keep the gamma the same. And we need to demonstrate that this is going to be a bounded linear functional. That's mostly because the mapping of g to its derivative evaluated at a point is also going to be a bounded linear functional, where we take a look at each one of these partial derivatives of g, and then we can recombine everything with the components of y and the various partial derivatives of g and turn that into a scalar mapping. And so then you have a functional mapping g to the, say, the gradient of g composed with gamma of t times y of gamma of t, and that turns out to be a bounded linear functional for each particular t in our time. And so then if we take the integral from 0 to t, it can also be shown that this is a bounded linear functional on g. Now the question is, what function gives us this particular functional? And then that'll tell us what the adjoint of our Liouville operator is on our occupation kernel. And it is going to be this right here, where you end up taking the gradient of the kernel function with respect to the second variable rather than the first, and then you multiply by this y of gamma of t, and then you integrate from 0 to t dt. And so then that tells you that this is going to be what the mapping is of our Liouville operator corresponding to some basis function y acting on our occupation kernel, and there you go. Okay, so before we start, there's something I need to tell you, and it's really embarrassing, but I made a mistake when I was recording the video. This is actually developing research and stuff that my colleagues and I are putting together right now. We are responding to a bunch of reviewers for a paper that we have at a major journal, and this is some theory that we're adding in there. Everything I'm saying is going to be absolutely correct if you make the change of adjusting every time I say inner product to pre-inner product. And now there's a very standard thing that we can do in Hilbert space theory to turn this from a pre-inner product to a proper inner product, and I'll tell you what that is after we go through all this discussion. It's infuriating because I was just finishing up writing this paper, and one of my colleagues came up to me and said, "Hey, this doesn't look quite right." He pointed out sort of the thorn in my eye that I was sort of ignoring. Ironically, this problem that we run into of being a pre-inner product rather than an inner product is something that I've called other researchers out in other contexts. It's frustrating that I miss this myself, but that's how research works. You get really attached to a theory and you get really invested until somebody tells you that you're wrong, and you go through stages of being very angry with them to being very thankful for them for finding out exactly what this issue is, and ultimately it leads to better theory. And so I'll tell you exactly how this leads to a stronger and better theory after we get through this whole discussion of constructing this pre-inner product. And I'll just put pre anytime I say inner product, just keep reminding you. But yeah. So let's go ahead and jump into the discussion, and then we'll come back here and I'll tell you exactly what went wrong and how we can fix it. So here's where the cool part comes in. If I take a look at the inner product inside a reproducible kernel Hilbert space, and I take a look at the adjoint of a Liouville operator corresponding to some, say, f acting on our occupation kernel with this trajectory gamma that we fixed ahead of time, and we take a look at the inner product against the adjoint of a Liouville operator corresponding to some other dynamics, say h, and this is acting on the same occupation kernel corresponding to gamma, then this gives us a well-defined inner product on the collection of dynamics that lead to densely defined Liouville operators over this reproduced kernel Hilbert space that we have fixed. So then, given this kernel space and this particular occupation kernel corresponding to some fixed trajectory, we now have an inner product space on the collection of dynamics, which is really cool, and it is honestly new. This is a work of me and my colleagues, Rishikesh Kamalapurkar, Benjamin P. Russo, and Taylor T. Johnson. So now what I want to talk to you about is how we can do projections according to this inner product using gram matrices. But the computation of these grand matrices are very, very tricky, and sometimes the weights you get out of them aren't going to be very good. And so we have a modification and a simplification of the problem that leads us to a parameter identification that is very close to the SINDI algorithm. And in fact, it gives us what we would call a weak version of the SINDI algorithm. Okay, so step one is to compute the grand matrix. So we're going to have a collection of basis functions, say yi, and each one of these basis functions give rise to a density-defined Liouville operator over our reproduced kernel Hilbert space. We have some unknown function that we would like to project down onto the span of these basis functions, and so to do that we need to use this inner product that we just made, and we need to make a grand matrix out of it. So the grand matrix is more or less what you would think. You would take all the pairwise inner products of these yi's and yj's, and you make a matrix out of them. Now, to compute these pairwise inner products, it ends up being a double integral of the gradient with respect to the first variable of the gradient with respect to the second variable of our kernel function at gamma t comma gamma tau of yi of gamma t and yj of gamma tau, and we're integrating this dt d tau. That gives you that one inner product, and it's kind of a bear to compute. So in order to find the inside of that expression, it takes a good amount of vector calculus, and I've computed it for, say, the Gaussian RBF and the exponential dot product kernel, and I'll put those here, and they're quite the monster. But ultimately we'll figure out another way around this problem where we don't actually have to compute this. And so then that's going to be our grand matrix, and that's multiplied by the weights that we're looking for. Now, on the other side, we need to take the inner product with our unknown dynamics f against each one of these basis functions. Now, f is unknown, and so that might lead us to a little bit of a problem as far as computing this inner product according to the way I just told you. But since f is supposed to correspond to the trajectory of the system, that means that that particular adjoint of a Liouville operator on this occupation kernel can be expressed simply as a difference of two kernel functions, where the two kernel functions are centered at the various endpoints of our trajectory, and that is data that is actually available to us. On the other hand, we do know what the adjoint of this Liouville operator is corresponding to each one of these yi's against our occupation kernel, and that was the expression that we just talked about earlier. So we need to take the inner product of these two things. That basically just means that we need to take the difference of the evaluations of the adjoint of these yi's applied to our occupation kernels, and that gives us a function, and we need to evaluate that function at each of the endpoints of our trajectory and take that difference, and that gives us a complete system of equations to solve to find the weights of the projection of f onto this basis. Now that's a bit of a mouthful, and we don't want to do it. And the reason why we don't want to do it is, one, it's really hard to code up that matrix for the grand matrix. In one case when I did it, it took 180 seconds for just a trajectory of only 300 points. And then I did it in a different way, and it got exactly the same matrix in half a second. Ultimately, I found that the weights ended up being a bit off. So me and my colleagues looked for a way of getting around this problem, and it comes down to looking at the features of our kernel function. Okay. So why don't we talk about what we need to do with these features and how it can make a better algorithm. So what we're going to do is we're going to take a look at the features that correspond to our kernel function. And so this is, remember, a feature map is something that takes elements of our domain, say x out of Rn, and maps it into an infinite dimensional space, L2 of n. And the kernel function itself is supposed to enact the inner product on this L2 space just by evaluating the points in our domain, x and y. If we go ahead and express our kernel function in terms of the features, we can actually take a different look at the adjoint of these Liouville operators on these occupation kernels. So to start with, remember that these occupation kernels can be written as an integral from 0 to t of k of x comma gamma of t dt. So it can be written in terms of our kernel functions. And so then if we expand the kernel function in terms of the features on the inside, that means that we can move the integral inside with a little bit of dominated convergence theorem. And then what we have is we have the features with respect to x being left alone altogether, and this integral is being applied to the features that corresponded to the second variable. And so now we have our feature corresponding to x times the integrals of our features composed with the trajectory. So now what we can do is, if we want to take a look and see what happens when we apply the adjoint of a Liouville operator corresponding to one of our basis functions, then all of that action ends up happening on the second variable and not the first. And so we can now just take a look at the integral of the gradient of our feature composed with gamma of t times y of gamma of t dt. And this feature is being multiplied by the feature evaluated at x, and then we're taking the sum over all of the features that map into L2. Now what's really cool here, if we want to take the inner product of our basis functions inside of this new inner product space that we have, all we now need to do is we need to take the pairwise products of the integrals of these features times our basis and take that infinite sum. And then that gives you the inner product there. And what this tells us is that we can take our gram matrix and we can actually rewrite it as the product of two infinite dimensional matrices. And in fact, each of these two matrices are the same matrix, but one is just transposed from the other. And these matrices are only infinite in one direction, so that when you end up taking their product, they end up giving you this finite gram matrix. Now, on the other side, where we don't have the gram matrix, but we have the evaluation of our unknown dynamics against each one of these basis functions, so then what we can do is we can take a look at this difference of kernels, and we can rewrite that as in terms of our features, where we basically have the sum of the feature which corresponds to x times the difference of the features that correspond to the endpoints of our trajectory. And so now when we want to take the inner product of the adjoints of these Liouville operators corresponding to our basis on our occupation kernels against this difference of kernels, then what we can do is we can go ahead and express this as an infinite dimensional matrix times this vector. And you'll notice that in both cases, we have the same infinite dimensional matrix on the left-hand side. If I remove that and we satisfy what was remaining, the ultimate result will satisfy the original linear system that we cared about. So now why don't we take a look at exactly what we have left over after removing that first infinite dimensional matrix. So what we have left over now is if we take a look at, say, the first row times our weights and equate it to the first row on the right hand side, then what we're going to have is we're going to have the sum of the weights times the integral of, say, the first feature evaluated at gamma of t times yi at gamma of t, and we're taking this entire sum, and this should be equal to the difference of our first feature evaluated at the endpoints. And so basically we're trying to find the weights that satisfies this linear equation. And now if we take enough features until we find a full rank matrix on the left hand side, now we actually have a way of determining exactly what these weights would have to be. We just want to make sure that the rank of that matrix on the left hand side matches the number of weights we have, and so then we can actually use something like a pseudo inverse in order to compute what the weights are. Now what's really interesting here is that if f was exactly in the span of these basis functions, then the left-hand side actually would come out by the chain rule. So for instance, if I were to take that, say, first feature and I composed it with the trajectory corresponding to our system, and then I took its time derivative, then I would get the gradient of that first feature composed with our trajectory times f composed with our trajectory. And that's the time derivative of our feature composed with the trajectory. But if f was actually in the span of this basis functions, we could then just go ahead and expand that out, and that's exactly what we would have gotten here with the first row on the left-hand side. So then that gives us two directions to arrive at the same point. We could have started with f being exactly in the span of the basis functions, rather than just trying to get this projection. And then we would have come down to a similar sort of problem here. Now, what mathematicians usually call this sort of thing, where you take a look at a problem, but you first compose that problem into another function, or you look at it through a collection of functionals, is we call this a weak formulation of a numerical problem. And so this actually ends up coming up a lot in the study of PDEs and a lot of other systems. In this case, we're going to have these features playing the role of what are called test functions. And interestingly, if we have a collection of test functions that we are really interested in satisfying this sort of parameter identification routine, then we can actually make a new kernel by using these test functions as features for a new kernel, and then that would give us a new inner product to do all this work on. And so this gives us a direct connection between doing, say, the sort of test function approach for parameter identification versus this inner product that we developed on dynamical systems that give rise to densely defined Liouville operators. And this gives us a great segue into talking about the Cindy algorithm and our own personal approach to this sort of system identification routine that we published back in 2019 at the CDC. Okay, So what's a pre-inner product versus a regular inner product? And so inner product has sort of this linearity in the first variable, conjugate linearity in the second variable, or if it's just a real valued inner product, it's linear in both. And it also has a sort of semi-definite property. So if you take a look at X inner product with itself, then you're going to end up with something that is either positive or zero. And an inner product is specifically the case where your inner product with yourself is zero, then you must be zero. And so a pre-inner product removes that last condition. And so you have some things that can map to zero when you take the inner product against themselves. And that runs into sort of this sort of indeterminacy that comes out of here. Now, there are ways of dealing with inner product spaces that arise from pre-inner products. And there's what methods of completing them into a proper inner product. For instance, in Wendland's scattered data interpolation, there's a whole chapter on positive semi-definite kernels, where he has to add on a few extra terms in order to take care of this sort of indeterminacy. Now, in our case, the indeterminacy can actually be infinite. So why don't we go ahead and talk about exactly where this indeterminacy comes from. So if you take a look at those forms I wrote for, say, the Gaussian RBF and the exponential dot product kernel, you'll notice that there's a matrix in between the two yi's and yj's, where this matrix is actually going to be lower bounded by the identity matrix. And we can show that the resultant norm from this pre-inner product actually dominates the norm that we get from the L2. When I say norm, I mean actually a norm in the L2 sense on this curve. So we look at each one of these symbols that gives us a densely defined Liouville operator, and we restrict it just to that trajectory, and then we can actually talk to it about an L2 space over that trajectory. And that actually gives you a proper inner product there. And what we want to do is we want to extend this result to not just match on the trajectory, but we want it to match for all of Rn. And so this is where we run into a problem. There's a lot of cases where a real entire function of several variables can actually be zero on this trajectory, but non-zero outside of it. And this inner product is like looking at these functions through a keyhole, and we're only looking at the keyhole that corresponds to this trajectory. So we have no way of discerning this function that could vanish at that trajectory itself. And so there's a couple of ways of handling this, and the typical way to do it is that we take a look at equivalence classes. We take this pre-inner product, and we take a look at every function from the space of functions that we care about, and we look at the ones that are sent to zero when you take a look at their inner product against themselves. And so then we say that a member of this new quotient space is going to be the set of equivalence classes where you can take a function from their collection of densely defined Liouville operators and then add on any one of these functions that are sent to zero. And so then we say that two functions are equivalent if you take their difference, and their difference is one of these things that are sent to zero by this inner product. And so this is the quotient space, and once you have that quotient space, this pre-inner product becomes a proper inner product on this quotient space, but you're still dealing with a lot of indeterminacy. One way to get around this indeterminacy is to make the assumption that we're in a parameter identification routine. So more than just doing a projection of f onto the span of basis functions, but declare that f is exactly the span of basis functions, and then there's no ambiguity. We know that f has to be coming from this. But in the case where we want to do a projection, f might be accompanied by some other function that is zero on this trajectory, and we want to be able to find some way of getting rid of that. Now, I mentioned earlier real entire functions sort of casually, but the truth is that the symbols for these densely defined Liouville operators, by the fact that they're densely defined over these particular reproduced kernel Hilbert spaces, say the exponential dot product kernel space and the Gaussian RBF space, it actually forces them to be real analytic functions over all of Rn. So these are real analytic functions of several variables. And so there's a theorem that comes with real analytic functions, and that theorem is called the identity theorem. It's actually easier to do over complex functions, but it still holds over the reals. So by thinking about the identity theorem, this gives us a different way of forming a proper inner product, and that's going to involve a whole lot of sums of these pre-inner products. And this is like something that happens with like the metric for the Schwartz space, where we take a whole bunch of pseudo norms and then we add them together until they're a proper norm, and we can do exactly the same sort of thing here. So how do we do it? The biggest issue here is that we're trying to identify a real analytic function of several variables in Rn using a one-dimensional manifold, and that one-dimensional manifold comes from our trajectory for this dynamical system. And so we would like to do better. If we look at the identity theorem for real analytic functions, basically we can show that if two real analytic functions agree over an open set inside of Rn, then they must agree everywhere. And so a one-dimensional manifold is not going to be an open set inside of Rn. We need an n-dimensional set in order to get this. Well, one way we can do this is we can add more trajectories. And so what we can do is we can take an open set of initial points for our dynamical system. It could just be some neighborhood of the initial set that we started with. And then we take a look at all of the trajectories that come out of that initial set, and then we take a look at the inner product that arises from each one of these trajectories. Now what's cool is that we can go ahead and we can integrate over all of these initial positions, and then what that ends up giving us an integral of all these pre-inner products, and then if we have agreement of two functions according to these new inner products that we're dealing with, then we can actually show that this is a proper inner product. But then from a computational point of view, what we really need to do is we need to go ahead and we need to take a discretization of that initial set, and then we get some sort of approximation of what this true inner product will be. So that's how you can turn this from a pre-inner product to an inner product. One we would use in the case that we have only one trajectory from our system, and then this would give us a quotient space that we would use as our inner product space as an alternative to the entire space of functions. Now we just take a look at them modulo functions that vanish on the trajectory. But if we want to make sure that we can stay inside the same space itself, then what we need to do is we need to consider more trajectories. So this gives us two routes to an inner product over dynamical systems that give rise to densely defined Liouville operators over these reproduced kernel Hilbert spaces. In any case, so I liked how I ended the last recording I did a few days ago, so I'm gonna chop back to that. And yeah, thanks for sitting in here with me. And yeah, this is how research goes. So if you like this sort of thing and you want to learn more about dynamical systems and data-driven methods and, you know, my own research, then please subscribe, and well, I'll see you next time.